Today we will be learning about a reaction turbine called as Francis turbine. Now what is a reaction turbine? First we should know a reaction turbine is a turbine which uses both kinetic and pressure energy of the water to run its blade. Now it's designed in such a way that it uses both the pressure and kinetic energy of the water. Now we should know what is the best way to judge a turbine. The best way to judge a turbine is through the momentum, which is nothing but torque generated by the turbine. Now we will try to find the expression for the torque generated by the turbine. Now we should know that this is a turbine and this is the outer parameter and this is the inner parameter of the turbine, and this is the inlet and this will be the outlet. So this is the velocities. I'll be telling what particular do they mean. So the water flows from this point to this point, from inlet to outlet, and through this procedure it loses its velocity, which is gained in the turbine to generate electricity or for whatever reason. So now this is the runner through which the water slides down, and due to the sliding motion of water the turbine rotates with some angular velocity, let's say omega. Now the water enters with the velocity v r. Now why v r? This is the relative velocity. The water will never enter in the same angle of the blade because it's always relative. So this is the relative velocity, and the water will always enter this turbine with the relative velocity v r. Now we have subscripts 1 and 2 for inlet and outlet respectively. So that is why 1 and 2. So we are here. Now this will also, at this point there must be a peripheral velocity. Peripheral velocity is nothing but with which this blade at this point have the tangential velocity. So this, let's call it as u1. I've written it as blade velocity u, and this is u1 because it ended. Now we will shift this velocity. The tail should be joined with the head of this vector to get the resultant velocity, which will be nothing but absolute velocity. So the absolute velocity of water at the inlet will be v1, and this will be this in this direction. So now similarly this will have peripheral velocity here, or I should say blade velocity, and relative velocity here, and we will shift this vector here to get the absolute velocity at outlet. So now let's try to figure out the expression for torque here. Now for torque, we should know that it's nothing but R cross F. I've also forgot to mention the radius here. This will be capital R here and small r here. This is the radius for the outlet, and this will be the radius for the inlet. So the torque will be rewritten as R momentum upon time, which can also be rewritten as m by t r cross v. This can be rewritten as m dot, which is nothing but mass flow rate. So we will be left with this expression. So now the change in this entity will be giving us the momentum, the torque. torque is equal to m dot, we will be finding r cross v, sorry, for inlet minus r cross v for outlet. For inlet, now also to note that what will be the v we will be considering for this expression. We will be taking the, let's also I forgot to mention one angle here, which is known as alpha. Alpha is nothing but the angle with which the absolute velocity makes with this blade velocity. Here it will be alpha 1, here it will be alpha 2. We always take the velocity component which is in perpendicular direction with r to find the torque. So for this, let's stretch this u because it's in perpendicular direction. So we'll be taking a component of v1 along this line. So what will it be called? It will be called v1. Since it's along this line, we will call it as cos alpha 1. And along this line, we will be taking the component of v2 here, which will be v2 cos alpha 2. Now for this same, we will rewrite this expression as m dot r, it's capital R multiplied by, this is not cross, this is multiplication, multiplied by v at inlet is v1 cos alpha 1 minus small r v2 cos alpha 2. This is the expression for torque we are getting. This will be the torque generated by the turbine. Now we have found out the expression for torque, and through this we will be calculating the expression for power. Now what is power? When we find torque, when force is the parameter, we say it is V cross F. Now since we are dealing with the rotational aspects, we will be replacing this as omega times torque. This will be converted to omega. This is omega, and this will be replaced with torque. Now let's multiply this expression with the angular velocity of the turbine to find power. If we will multiply this with omega, we'll get an expression like omega r v1 cos alpha 1 minus omega r small r v2 cos alpha 2. Now we can write what is omega capital R. Omega into capital R is nothing but the blade velocity u. Now since it's capital R, it will be u1 and v1 cos alpha 1 minus, it will be converted to u2 now v2 cos alpha 2. Also this term v into cos alpha, v1 cos alpha 1, v2 cos alpha 2, this term is known as swirl component, or you can say swirl velocity. This can be represented through v u1. Why u we have taken here? Because it's along the direction of u, along the direction of blade velocity, minus u2 v u2. Now this is the expression for the power generated by the turbine. Now we have found out the expression for power generated by the turbine, and this equation is is also Euler's equation, which is a very well known equation for fluid machines. We will try to rewrite this expression in another form now. What is power? Power is nothing but work done upon time. And work done, what is work done? The work done is nothing but the energy which the water is holding in itself. So this will come through the energy of water, which is mgh upon time. We can rewrite m upon t as m dot gh, and also when we are finding the power generated by the torque, we are taking an ideal case, so the height which we are taking will be the ideal one. Let's call it as Euler height, because we are manipulating this equation only, this equation only. So let's call it as HE. We can now equate these equations. So if we equate this equation, the m naught will be cancelled out, and we will be able to get this expression as, let's write it as capital H. HE is equal to U1 V U1 minus V2. Let's write in similar fashion only, U2 V U2. This is the expression we are getting, and we can write it in this form: U1 V U1 minus U2 V U2. This is the expression we got, and this HE is nothing but Euler's height. Because when we actually design and have an application of the turbine, the height which is available, the actual height which is available for the turbine is greater than this energy, because this energy will be, the ideal one will be always less than the actual. If the turbine is really efficient, it could be equal as well, but there are no such cases which we have seen an efficiency of 100%. So we just call it as H, or you can say H actual. And why is it so? Because it's inefficient, because there are many losses which we will be discussing later. Now we have found out this expression for Euler's equation, this form of Euler's equation we've got, and we will try to deduce another way of writing it. Let's try to draw the velocity triangle at inlet. This is plate velocity U, this is relative velocity Vr, this is the absolute velocity, this is the resultant of these two vectors. And if I'm drawing for the inlet, we will write subscripts 1 at each variable. What? Now I forgot to mention the alpha angle, which is also known as guide vane angle, and we will try to look at this triangle. If this is U, this will be the component of V1 cos alpha 1. If this is U and this is V1 cos alpha 1, this will be U minus V. Also, I could have rewritten as V U, or if I should write 1 as well, U1 minus V u1. Can I write it like this? This length will be, this length of velocity will be this much, and this is perpendicular, and this is nothing but Vf, which is the horizontal component or vertical component of V1. Let's write it as Vf1. Now let's look at this triangle. We will use Pythagoras equation in this one. So this would be V R1 square is equal to U1 minus V U1 whole square plus this is V F1 square. Let's open this bracket. U1 square plus VU1 square minus 2U1 VU1 plus VF1 square. Now V velocity is nothing but the component of the swirl component, which is VU, plus the radial component VF. So we will replace this VU1 and VF1 square quantities with V. The video got cut by mistake. So let's continue and let's try to rewrite this and this with V. U1 square, this and this will get reduced to V square, V1 square, because we are talking about the inlet here. So this will become minus 2 U1 V U1. Similarly, we will get expression for outlet. This is for inlet. If we write it for outlet, this will become, the subscript will become 2. V2 square minus 2 U2 V U2. Now we will try to get the value of these entities. And why? Because these entities look similar to entities used here. These entities, if we try to get for this expression, then U1 V U1 will become V R1 square plus, sorry, I'm writing mistakenly. This will come here and this will go there. So this expression will become U1 square plus V1 square minus VR1 square upon 2. And similarly, we will be able to get expression for outlet. Let's first try to, let's write for outlet as well. U2 V U2 is equal to U2 square plus V2 square minus VR2 square upon 2. So we will put these values in this expression and we will get HE is equal to U1 square plus V1 square minus VR1 square upon 2G. I'm writing the 2 and the G here as well, minus this whole expression, because there's a minus there and this minus is here, and this will become U2 square plus V2 square minus VR2 square upon 2G. Now, if we club the similar terms together, we will get the expression as HE is equal to U1 square minus U2 square upon 2G plus V1 square minus V2 square upon 2G plus VR2 square minus VR1 square upon 2G. So now this is the alternate form of Euler's equation. Now we got three entities here. In next video, my friend will be explaining what these three entities denote. What does it denote from the Euler's equation? Thank you so much for watching.
My name is Naman Sabarwal, roll number 167. I will be moving on with the next topic, that is nature of energy transfer, which I will be just explaining. Now we'll move on with the next topic, which is nature of energy transfer. The expression for Euler head for HE in the form of 2.12, which we have discussed previously, is given as follows: V1 square minus V2 square divided by 2G, and VR2 square minus VR1 square divided by 2G, and U1 square minus U2 square divided by 2G. Now we all know that V square by 2G represents the velocity head of the absolute velocity. Therefore, it is nothing but kinetic energy per unit weight of water in a designated section. Thus, the first term V1 square minus V2 square, it represents change in absolute kinetic energy between inlet and outlet of the wheel. This is called as impulse effect. Then we have to consider the energy equation in the form of a Bernoulli equation, because it is an incompressible and frictionless flow between sections 1 and section 2. And the amount of energy head HE has already been extracted out of the flow between the two sections. The energy equation can be written as follows. That is V1 square plus P1 divided by sigma, V1 square divided by 2G plus P1 divided by sigma plus Z1, which is equal to V2 square divided by 2G plus P2 divided by sigma plus Z2 plus HE. Now we have to just simply replace HE with V1 square minus V2 square divided by 2G plus with the rest of the equation which we discussed previously. Sorry for that. We know now H1 minus H2 represents a change in piezometric head between sections 1 and 2. Now in turbine setup, the term Z1 minus Z2 is 0 or negligibly small. Hence the terms on the left side, 2.14, equation 2.14 represent essentially a change in the pressure head. Thus for second and third terms, 2.12, VR2 square minus VR1 square divided by 2G, and U1 square minus U2 square divided by 2G represents change of energy in the form of pressure head. The second term, VR2 square minus VR1 square divided by 2G, could now be interpreted as the energy change in the form of pressure head due to the acceleration in convergent passage. If the passages are divergent, there will be deceleration in an inward flow runner. The flow passages decrease from the inlet to the outlet, and usually VR2 is greater than VR1, and as such the term VR2 square minus VR1 square divided by 2G represents a decrease in pressure at 2 from that at 1 due to acceleration of the relative velocity. Then in the third term, U1 square minus U2 square divided by 2G represents the pressure head change due to centrifugal effect. The velocities U1 and U2 being peripheral velocities at inlet and outlet, they represent the velocity head of forced vortex. Note that in an inward flow reaction turbine, U1 is greater than U2. Hence, U1 square minus U2 square by 2G is a positive quantity. On the other hand, in an axial flow propeller type turbine, U1 is equal to U2. Hence, U1 square minus U2 square divided by 2G will simply become 0. The sum of the second and third terms of equation 2.12 will be summed, and then it will be given as follows: VR2 square minus V1 square divided by 2G plus U1 square minus U2 square divided by 2G, which represents the change in static pressure head in the system, is called the reaction effect. So now we know what reaction effect is. So the relative values of impulse effect and reaction effect in the energy head HE of a turbine forms an important aspect in the design of the rotors. The ratio of reaction effect to the total energy transfer in the rotor is defined as the degree of reaction. Thus, by considering unit weight of water flow in the turbine, so unit weight of water flow in turbine is nothing but degree of reaction. That's what it's simply trying to say. So degree of reaction is after all the calculations and everything, it's shown as VR2 square minus VR1 square divided by 2g plus U1 square minus U2 square divided by 2g divided by HE, which is equal to HE minus V1 square minus V2 square divided by 2g divided by HE. Now a turbine rotor with a now here it's shown that it's explained that a turbine rotor with a non-zero degree of reaction must necessarily be completed enclosed for development of pressure head. Such turbines are called as reaction turbines. If the degree of reaction is zero, the rotor can be open to atmosphere. Such turbines are called as impulse turbines. In a pure impulse turbine such as Pelton V, there is no reaction effect leading to R is equal to 0. Hence, in these units, the rotor is not encased to contain any water under pressure and the pressure is atmospheric everywhere. Thank you, sir.
Hello everybody. I hope you are doing well. As it has been mentioned by my classmate, we are working on the topic of France turbine, and I'm going to continue on the path of hydraulic efficiency. However, the definition of hydraulic efficiency in France turbine state that it is the ratio between the runner power to the shaft power. So today's globally competitive business world drive manufacture to get the most of their equipment. Even small increase in machine productivity that can mean the difference between profit and loss. Additionally, environment concern demands focusing on sustainable business practice and energy efficiency system. So in response, industrial and mobile equipment hydraulic system have become smaller and lighter and utilize higher pressure to achieve maximum system efficiency. Now, advanced hydraulic fluids are available to meet the demand of this system, as well as to contribute the overall hydraulic system and energy efficiency. So in theory, hydraulic system convert mechanical energy input from an electric motor or internal combustion engine into fluid flow. So and then pressure that can accomplish a specified amount of work that can accomplish a specified amount of the work. So hydraulic pumps convert the mechanical energy of the prime or mover into the flow, into fluid flow. So pressure is generated by the restriction of this flow in the system. So the hydraulic efficiency of the turbine is given by NH, which is head extracted by the rotor divided net head available to the rotor, which can say HE divided by H. What does mean by H? What does mean by HE? HE is the net head available to the rotor, and HE is Euler's head. So in practice, it has been found that expect for a very small river swell that may be advantageous in increasing the Euler's head. Presence of negative swell in the outlet flows causes the efficiency to drop very rapidly. So this is because large rivers swell cause a large amount of kinetic energy in the existing water, and hence in the reduction in the utilization of the available head. So I'm going to let my partner or my classmate to continue where I have left.
Naveen, my roll number is 2K20 ME 170, and today we are discussing about Francis turbine. First, we draw the figure of Francis turbine. With the help of this, we learn this. First, we draw pump and these are the runner, as you can see. These are the runner, these are the guideways which behind the runner, and is water from penstock. So water enters from this and goes through this, and the area is reduced. You can see here, area is lesser than this, and after that free surface of water. This is the free surface of water, and these are the fluid goes outward directions, you can see. So firstly, the Francis turbine is a reaction flow turbine. Firstly, reaction flow turbine, in which kinetic energy and pressure energy enters the turbine. This is the first point. Now secondly, it is a mixed flow turbine. And in mixed flow, water enters from the penstock in the radially and leaves axially. You can see, enters from here radially and axially leaves. And it has also third point, it has medium head. Francis turbine has medium head, and there is a medium quality of water. Medium quality of water, and one more point is that it is a medium specific. It is a medium specific point. Medium specific speed, and there are some of components are firstly the spiral casing, secondly the penstock. In this part, the top view is spiral casing. In this part is called spiral casing, and third is the guide blade. And runner, and the top view, this part is known as a runner, and draft tube. Now firstly, here we are making the spiral casing diagram. So roughly I will explaining this. So here is spiral casing have maximum area at the entrance, as you can see, and nearly zero at the tip. And area of spiral casing decrease uniformly along the circumference, and water from the penstock through the guide veins uniformly distributes over the runner veins. And these are the spiral casing, and these are the runner wave, and these are guide blade. And that is
Good morning, sir. My name is Nazim and my roll number is 2K20 ME173. Previously, Naveen explained the concept of Francis turbine and the diagram and explained the sum of the component of the Francis turbine. Like he's explained that spiral casing is a one of the component of a Francis turbine and steering. Now my turn to explain the concept of the adjustable guide wheels, which is also known as the wicket guide. So the guide wheel is also known as the wicket gate. The main function or the usually of a guide wheel are the guide the water towards the runner. The water flow must be a angle and must be some inclines, and that is the appropriate for the design. And the next component is a runner bladder. The runner bladder design describe how the efficiency of a turbine is go perform and go very well. The runner bladder are divided into the two parts. So first one is the lower half of is made is the shape of a small bulk bucket. So that is use the impulse action of the water rotate the turbine. So the basically the first part is helping to the rotate the water of the turbine. And the upper part of the bladder is used for the reaction force of the water flow through it. There are the two forces to make the runner bladder. And we go through the next topic, and which is the draft tube. Draft tube is one of the component of the Francis turbine. The draft tube is the expanded tube which is used to design the water through the runner and the next to the tail rings. Basically, the main function of the draft tube is to reduce the water velocity at the time of a discharge. So the meaning of that this line is the main function of the draft tube, basically the reduce the water velocity at the time when the time of the discharge, when the process in the discharge, and its cross section area along with its length, as the water coming out of the runner bladder is at considerably low pressure. So it is expanding the cross section area, that is common thing. It, it recover the pressure as the flow towards the tail ring. And there are some figures which is given in the book. We follow and we understand what is this. And so the first one is a systematic sketch of a function of adjustable guide wheels. Yes, and this is the upper and the lower part of Francis runner. Now, in the topic of draft tube, I highlight such 2 points, which is for me is important for the student. The point is the draft. The first point is to enable the turbine to the setup at the elevation higher than the tail rail level. And the second one is utilize a major part of the kinetic energy of the water extending the turbine. So our the next topic in next component is a governor. The governor of a turbine is defined as the operate by the which is the speed of a turbine is kept constant under the all the working conditions irrespectively of the load variation. The governor of a turbine is necessary as the turbine is directly coupled to the any electrical motor which is required to run at any constant speed under all the fluctuation load condition. It maybe can be called as the concept of the flywheel is derived from that statement. And we go through the next point. It is done automatically by the mean of a governor which regulate the rate of a flow through the turbine according to the change load condition on the turbine. The governor used in the hydraulic turbine should is very stronger as it the deal with the water coming at the very large force and the quality. That is the importance of the governor in the Francis turbine. Thank you all of you, and thank you, sir.
Hello everyone, my name is Naveen Shah, roll number 2K20 ME171, and my topic is working proportions of a Francis turbine. Shape and working proportions of a Francis turbine. In this section, we will discuss about shape and working proportions, and these working proportions are also called design parameters of Francis turbine. We will look into these parameters. So before discussing the parameters, we will look into the variables which are responsible for these parameters, like H, which is the net head on the turbine, and rotational speed of the vane, which is obviously should be in RPM, and P is the power developed by the turbine. Ns, which is the specific speed, D is the diameter of the vane, and B is the width of the runner. This B can be also divided into two parts, which is B1 width at inlet and B2 which is width at outlet. If you don't know about this Ns, which is specific speed, then it is nothing but the speed of turbine at which it would produce unit power when working under unit head. This is the specific speed. It is independent of the size and used to select the type or which shape of the runner, generally given by the formula here. N denotes again the rotational speed of the vanes, and P is the power, and H is the total head. Now these N, H, P and D, B variables plays important factor for the shape of the runners in Francis turbine. The geometry should be in a such a way that the runner should be able to handle the increase in discharge without choking. So parameter like flow ratio, speed ratio, that helps to choose the diameter node geometry of the vanes properly. Now we will look into some parameters. Now we will look into these parameters. The first one is relative guide vane passage size. It is denoted by N. N is the ratio of B by D. B is the width and D is the diameter. So this vane passage size is the strong function of a specific speed, and its value generally ranges from 0.1 to 0.75 range values. So that is, if Ns increases, N also increases. In low head turbines have high values of B1 by D1, that is relative guide vane passage size. Low head turbines have high values of N. Now the second parameter is the speed ratio, denoted by Ku. Speed ratio generally tells us about the relation between the peripheral velocity, that is U1, and the net head of the turbine, that is H, denoted by U1 equal to Ku under root 2 GH. Now here, if we look carefully, we can see that our U1 is directly proportional to root H, and the root H is root H gives the idea about that it is a function of a specific speed. So it is also function of specific speed. Its values ranges from 0.72 to 0.82. Generally, it is a weak function, so it value not much ranges. Now the third parameter is the flow ratio, denoted by Kf. Flow ratio only comes in consideration when the velocity of flow remains constant. Velocity of flow constant, which means the flow velocity at inlet should be equals to flow velocity at outlet, and this will be equal to Kf under root 2gh. It is also a function of specific speed, because here we can also see that the root h comes into the picture, so it also varies with ns, but it varies linearly, and it values ranges from 0.15 to 0.30. The fourth parameter is vane thickness coefficient. Which is denoted by K. We know that the area of the veins are usually given by A equals to pi d1 b1 minus mt b1. Here d1 is the diameter of the vein at inlet, b is the width of the vein at inlet, c is the thickness, and m is the number of veins. But when we are considering the vein thickness coefficient, then this formula can be reduced into A1 equals to K1 pi D1 B1. This suffix 1 here is for inlet. So general formula is A equal to K pi dB. And K here again vein thickness coefficient. Its value is generally taken as 0.95, because at this value it gives up the appropriate geometry for the runner. There are some other parameters as well, like solid exit, guide vane angle, and output angle. Then these parameters will be explained later by my teammates. Thank you.
Hello, I'm Navneet Kumar, roll number 2K20 ME 172. I will be continuing with the parameters of Francis turbine, which my friend Naveen Shah was talking earlier. One of the parameters is no swirl at exit. It is generally assumed that in the Francis turbine, the flow which is exiting is purely radial and there is no swirl velocity at the exit. It can be seen in the outlet velocity triangle of the Francis turbine, which I am going to show you now. This is the outlet velocity triangle of the Francis turbine. Here, V2 is equal to Vf2. That is, absolute velocity V2 at the exit is equal to flow velocity at the exit. Here, one of the component of the absolute velocity is the swirl velocity, which is said to be 0 in the case of the Francis turbine. Thus, these two become equal. Also, one of the notable point here is that this angle beta 2 is always less than 90 degree in the outlet. Now let us move on to our next parameter, that is guide vane angle. This is the inlet velocity triangle of the Francis turbine. And at the entry of the water in the runner, we want that it should enter without any shock. For this to happen, the absolute velocity V1 is guided inside by a guide vane angle alpha 1, such that the relative velocity VR1 meet the runner blade tangentially, and this angle beta 1 is called the blade angle, and this angle alpha 1 is called the guide vane angle. Now let us move on to our next parameter, that is classification
based on the speed. Here we can see three cases. First case in which angle beta 1, which is the blade velocity, angle beta 1 is more than 90 degree. Second case where the blade angle is equal to 90 degree. Third case where blade angle is less than 90 degree. These all changes from obtuse to acute with the range of specific speed of the Francis turbine. The data can be shown above. Here, when the range of beta 1, that is the blade velocity, blade angle, is from 90 degree to 120 degree, it is categorized as slow Francis turbine, and the range of the specific speed is 40 to 120 rpm, and so is the range of alpha 1 15 to 25 degree. As the range of beta 1 is changing, range of alpha 1 is also changing, and thus the category of Francis turbine is changing. When the range of beta 1 decreases to 90 degree, it becomes a medium or normal Francis turbine with a range of specific speed from 120 to 200 rpm. And when the range of specific speed is more than 200 rpm, it is categorized as fast Francis turbine with a range of blade angle 45 degree to 90 degree, and the range of alpha 1 is 32 degree to 40 degree. Now let us move on to our next parameter, that is number of guide vane blades. Usually the number of guide vane blades are in even, but its number is also changing with respect to the specific speed of the runner and the diameter, the inlet diameter. As it can be seen in this table, when specific speed is less than 200 rpm, its diameter is up to 200 millimeter. The number of guide vanes are 8. And when the diameter changes from 250 to 400, the number of guide vanes required are 10. And similarly, we can see for 12, for 14, for 16, and 18, etc. Similarly, in the case when the specific speed is more than 200 rpm and diameter is up to 300 millimeter, number of guide vanes is 8, and so it changes with 300 to 450 millimeter, the number of guide vanes is 10. When it changes to 450 to 750 millimeter, the number of guide vanes is 12. Similarly, 14, 16, 18, etc. At last, I would like to tell about some basic functional and geometrical relationship in the Francis turbine. In the Francis turbine, this inlet with this velocity u1 is r1 omega. Omega is the angular speed of the Francis turbine, and this u1 is equal to r1 omega. We can write omega as 2 pi n by 60, which concludes that u1 is equal to pi d1 into n upon 60, and n is the speed in rpm. Similarly, u2 can be written as r2 omega, which will lead to pi d2 n. d2 is the diameter of the outlet at the outlet, and d1 is the diameter at the inlet. And now we can talk about the hydraulic efficiency also by seeing this velocity triangle, as we are provided with here VU1, that is a flow velocity at inlet, and U1. The formula for the hydraulic efficiency is U1 dot VU1 minus U2 dot VU2 upon GH. As we know that the flow velocity at the outlet is 0, so the second term, which is having VU2, is cancelled out to 0, and we are left with U1 and VU1. Until unless it is specified, till then, the VF1, that is flow velocity at the inlet, and VF2, that is the flow velocity at the outlet, they both are considered equal. For inlet and outlet velocity triangle, we can also find tangent of these angles, like we can find the tangent of this alpha 1, that is a guide vane angle, as its perpendicular divided by base, which is VF1, the flow velocity at inlet, divided by the swirl velocity at inlet. Similarly, we can find for tangent of beta 1, that is tan of beta 1, Vf1 upon u1 minus Vu1. Similarly, for beta 2, we have found above that it is Vf2 upon u2. Thank you.